so here we go. This is just a little brief on the objectives for alcohols. It says identify the presence of the hydroxyl functional group, relate the properties to their functional group, and explain how ethanol can be prepared from ethene and from the fermentation of carbohydrates. And this is a common question that we see on the past paper as well, the fermentation of carbohydrates, as well as the steps and all the apparatus that are used for fermentation. It also says we're going to describe the reactions of ethanol, so combustion, and reactions with metals and also oxidation reactions, and we're going to state the uses of alcohols and also what happens when we abuse alcohol usage. All right, now for introduction, it says alcohols or alkanols have the hydroxyl group, the OH minus, as their functional group, and that's something that we know. The functional group for alcohols are OH minus. The name is here. I wish I didn't have the name, but since it's one carbon, this is what we call methanol. Remember, one carbon is meth, right? All alcohols undergo similar reactions because they all contain the hydroxyl OH group, right? So the reactive part of alcohols, they all contain the hydroxyl group, so they react very similar. Remember that the functional group is what give them similar reactivity properties, right? Or reactive properties, I should say. The strength of the reaction decreases as the number of carbon atoms per molecule increases. Does anybody know why? Does anyone know why the strength of the reaction decreases as the number of carbon atoms per molecule increases? I'm gonna allow you guys to, if you're here, I'm gonna allow you to look for it. You can search on Google and let me know.
What was the question, Miss?
Why is it that the reactivity decreases as the number of carbon atoms increase?
My gosh.
Yes, anybody found anything? Alright, so the main reason is because once you're adding more carbons, the carbon and hydrogen bond, the hydrocarbon is very nonpolar, and the more carbons you add to the molecule, the more nonpolar the molecule is, and the less likely it is to even give up its proton, this hydrogen here, the less likely it is to give up the hydrogen, or the less likely it will be dissolved in water. Remember that for something to be able to dissolve in water, it must be considered as polar, it must have free ions, right? And in the case of alcohols, when we increase the number of carbons, the non-polarity of the compound increases, which means it gets less polar, and so it becomes less reactive. So the more carbons that we have, the less polar it becomes, and the less reactive it also becomes. All right, moving on. So this is saying which one reacts faster, ethanol or, and I would like for you guys to actually name this alcohol here. So I'm just gonna put on my, what's the name of that alcohol on the right?
Is the one with the 9 carbons?
You said that reacts the fastest or the slowest?
Oh, slowest.
Yes, that would react the slowest. I'm trying to find out my tab. Right. So remember that the more carbons you have, the less reactive the alcohol is. So the one with the 9 carbons, what would you call it? Want to take a guess?
For some reason, I can't remember what 9 is. I only remember in decagon. I don't remember what 9 is.
So 9 is non. It's gonna be non-nanol.
No, no, no. Okay.
Yes, that's it. Alright, so we have non-nanol being the least reactive one here. Alright, just give me a second. I'm trying to send
Oh, no.
a message forward. I keep losing my tab. Right. So alcohols with three or more carbon atoms show structural isomerism. Do you remember what structural isomerism is? What is structural isomerism? All right. So structural isomerism, it really means, or structural isomers, these are compounds that have the same molecular formula but different structural formula. Right, so this says that alcohols with three or more carbon atoms show structural isomerism due to the change in the position of the functional group. So the OH can actually be shifted to carbon number 1, number 2. That gives some form of structural isomerism. And also we can have branches whenever we have more than 3 carbons in the alcohol. That also gives us structural isomerism. Right, so this says structural isomerism refers to the isomers with the same dash formula but different arrangements of dash and dash. Okay. So structural isomerism refers to the isomers with the same molecular formula. But different arrangements of what? So we could just have different structural arrangements or different arrangements of bonds and atoms. That is structural isomerism. Someone who just joined, your microphone is open. Right. Now this is saying what is the structural isomers of butanol. I'm just gonna do one. I believe I can allow permission for somebody to draw, but I'm just gonna do one. So butanol, but means 4 carbons. It's gonna be 1, 2, 3, 4, and I'm gonna put the OH here. So this is going to be called 1-butanol. Since the OH, the hydroxyl group, is on carbon number 1. So it's 1-butanol. Does anybody want to suggest how I could make another isomer of butanol? Alright, So for the other isomer, we have position isomerism that we can do where we change the position of the functional group. So in this case, the hydroxyl group is on carbon number 1, so I can change it to carbon number 2, and that would give me a different isomer. I'm not going to draw all the hydrogens in this case, but they're there. Just going to draw the next one right here. So it's 1, 2, 3, 4, and then the OH on carbon number 2. So that's another isomer with the hydrogens, of course, being here. That being position isomerism, where I change the position of the hydroxyl group. I could also do another isomer where I include a branch. So in this case, I could just draw 3 carbons. Remember, we need to have the same number of carbons. So I'm just going to draw 3 carbons, put my OH anywhere I would love to, and then I put a branch on the second carbon. This is also an isomer, right? And a good way to know if your structures are isomers is if they have different names but they have the same number of atoms. So they have different names but the same number of carbon atoms, same number of hydrogens, and the same number of oxygens. So in this case, the name of the second one, it is going to be, if we're going from the suffix tells us the functional group. We have alcohol, so it's going to be anal, and since it's 4 carbons, the prefix is going to be butanol, and we need to identify the position of the alcohol as well. So it's going to be on 2, it's going to be 2 butanol. Remember that we try to give OH the lowest possible number on the carbon chain, so it's going to be 2 butanol. In the case of this one, it's still going to be anal since the functional group is alcohol, and it's 3 carbons on the main chain, so it's going to be propanol. I also need to identify the position of the alcohol on the propanol, so it's going to be, this is carbon number 1. It's going to number them, carbon number 1, number 2, number 3. So it's 1 propanol, right? And in front of this, we need to identify our branch. The type of branch that we have is methyl. And the position of the branch is on carbon number 2. So the name of this isomer here, it's 2-methyl 1-propanol, right? Once again, if you need to know if an isomer, or if the substance or if the compound is an isomer, you can look at the name and also the amount of atoms that they have. If they have the same number of atoms but you get a different name or a different structure, therefore it's an isomer. All right. Okay, so those, I would have drawn some of these here. All right, now we're looking at the
Excuse me,
properties.
miss.
Yes,
Miss, how you get methyl again?
the five where?
Miss, methyl. I'm talking about the part that you
Oh,
have methyl.
methyl. Okay. So methyl, it's the branch. Remember, your alkyl groups are branch groups. They are not a part of the main chain. So the main chain being the longest chain, the longest straight chain. This is 1, 2, 3 carbons. This is the longest chain here, right? And on this longest chain, we have our alcohol here, and we also have our alkyl group here. Now, because this alkyl group has only 1 carbon, that is why we say it's methyl. If the branch chain was 2 carbons, it would have been ethyl. If it was 3, it would have been propyl, and etc. So that's how I got methyl.
Okay, miss, thanks.
Okay. Alright, so properties of alcohols. Alcohols are generally colorless liquids at room temperature. That's something that we know. Just think about your regular rubbing alcohol, ethyl alcohol. It's colorless at room temperature. The green ones is really just persons adding scents to the alcohol or adding different fragrances to the alcohol. to give it a enhanced property, of course, because I think the green one has probably mint in it or something of the sort. So they also say that alcohol molecules are polar due to the presence of the OH, the hydroxyl group. Remember that polar means that you have some partial charges present. That's something that you would have learned in grade 9. You have some partial charges present, as you can see here, with OH in this covalent bond. Covalent because we have two nonmetals here. In this covalent bond, even though they're both sharing electrons, so we have an electron pair being shared here, but even though they're both sharing electrons along this bond here, the electrons lean closer to the side that is more electronegative, right? That's under, I believe, periodicity in the syllabus, right? So the electrons lean closer to the side that is more electronegative, the side that, or the atom that will attract the electrons closer to itself. So we have one side being, or we develop poles basically because the electrons are moving closer towards one atom. We form poles, and that's how the oxygen gets a partially, it's not negative, it's not an ion, we say that it's a partially negative ion, or partially negative atom, sorry, and the hydrogen is a partially positive atom, right? And because of this, we say that the hydroxyl group here is polar. It's polar because of the oxygen and the hydrogen present. Oxygen being a bit more electronegative than the hydrogen. It's not something that you really need to know, but I'm just explaining it so you understand a little bit about poles, how the poles work. So polarity occurs since the molecule have a slightly positive and negative charge, as I would have said up here. Note that this part, the hydroxyl part of the alcohol, is polar. The reactive part of the alcohol is the hydrogen, right? And the rest of the molecule is non-polar. So all of this, the hydrocarbon, this is non-polar. So you have one part of the alcohol being polar and the other side being non-polar. Now, let me continue. All right, now this, we're under the volatility, which says the volatility is the ease with which alcohols are converted to vapor. And it's not just about alcohols. Volatility, we're talking about compounds in general, right? So it's how easily a substance evaporates. That's volatility. And if you think about alcohol, if you were to put a drop of alcohol on a table, it would be evaporated in about 2 minutes or less, right? That's how volatile alcohol is, and you can compare it to water. Water takes a very long time to evaporate, so we say that water would be less volatile, right? So alcohol is actually very volatile. However, alcohols are less volatile than their corresponding alkanes, right? Alcohols are less volatile than alkanes because of the stronger polar alcohol attraction.
Excuse me, miss.
Yes,
Miss, like we can send out the link so anybody can join.
sure, no problem.
All right, miss.
Mm-hmm.
Miss,
Yes.
11 hours of them are in math class.
I'm told that you have a math class now.
Yes, miss.
Okay, it's recording, so I'm gonna upload it afterwards.
Okay, miss.
Yes.
Tell them that?
Yes, you can.
Okay.
Right. So let me just say this again. For alcohols are less volatile than alkanes, which means that if you were to put an alkane, just a drop of alkane on a table, it's going to evaporate even more quickly than alcohols, right? And the reason for this is because alcohols have a polar group. The polar group here, this polar group here, the hydroxyl group, makes the alcohol very polar, and it also has a very strong force of attraction, making it less easy to be evaporated compared to alkanes, which only have hydroxyl group. So let me just draw the corresponding alkane here so you can actually see. So the top one would have been ethanol, 2 carbons, so it's ethanol. And this right here is ethane. I'm just going to repeat it once more. Um, Repeating it once more. So carbon, the alkane is more volatile than the alcohol because the alcohol has a very strong force of attraction inside the hydroxyl group. And that's just it shortened in one sentence. Right, and as you can see, this alkane doesn't have any hydroxyl group, so it would be more volatile. Let me ask you the question to see if you're paying attention. If we had something like a carboxylic acid, do you think it is going to be less or more volatile than alkane?
It will be less, miss.
It would be less, yes. Thank you. So it would be less because of the hydroxyl group that is present. All right, I'm going to move on.
Solvent. Oh.
Miss.
Hydroxyl.
Miss Higher.
The solubility of alcohol in water decreases as the hydrocarbon chain length increases.
Less.
Less.
Miss Incomplete.
Combustion.
Miss, could it be incomplete?
Miss CH3C2OH.
The double bonds. Saturated is alkane.
Hey guys, and welcome to the Chemistry Shack. In a previous video I made aluminum oxide. In this video we will be using that aluminum oxide to dehydrate ethanol in order to make ethene gas. Ethene is the simplest alkene, which is basically just a class of molecules containing carbon-carbon double bonds. It has the formula C2H4, and unlike ethane, which has the formula C2H6, you can see that ethene only has 2 hydrogens on each carbon and a double bond between the 2 carbon atoms. Because of the relatively weak double bond, ethene is much more reactive than ethanol, so it is easier to convert it to other molecules. The reaction we will carry out to produce ethene is known as a catalytic dehydration. The word catalytic, as you may be able to tell, indicates that we will be using a catalyst to facilitate this reaction. In this case, the catalyst is the aluminum oxide that we prepared in a previous video. The word dehydration indicates that we are removing a water molecule from the ethanol. In the equation on the screen, you can actually see where all of the atoms in the water come from. The OH of the water comes from the OH on the ethanol, and the other hydrogen atom comes from one of the hydrogens on the other end of the ethanol molecule. Together, these form H2O, and the 2 carbon atoms join together in a double bond. Anyway, that's enough with the theory, so let's get on to the actual reaction. Start by adding a few milliliters of anhydrous ethanol to a test tube clamped to a ring stand. Then add some of the aluminum oxide catalyst above the ethanol. Since we want the ethanol vapors to pass over the catalyst, it's important that the catalyst isn't submerged in the ethanol. Next, add a 1-hole rubber stopper with a glass tube in it to the test tube. Attach a plastic tube to this glass tube. Insert the other end of the plastic tube into a tray full of water. Now you will need to fill a test tube with water and insert it into the water tray upside down, securing it in place with a clamp. Make sure to leave some space at the bottom. This will be used to collect the ethene gas by water displacement. Begin the reaction by heating up the aluminum oxide catalyst. Keep most of the heat focused on the catalyst, but occasionally heat the ethanol for a couple seconds. Initially, the gas produced will just be air, but once ethene is produced, you will be able to smell it. I seem to be incapable of putting its smell into words. It's sort of like camping gas, but a little sweeter, I guess? Anyway, you'll recognize it when you smell it. Once you smell ethene, insert the plastic tube into the inverted test tube and collect the gas. An interesting side note is that the aluminum oxide catalyst turns black as the reaction progresses. I actually don't know why this is, and any suggestions in the comments would be pretty helpful. Anyway, we can show that we've made a flammable hydrocarbon by testing for flammability. I did this experiment again and collected another test tube full of ethene. You might be wondering, how can we be sure this is ethene and not ethane? Remember how I said earlier that ethene is more reactive than ethane? Well, we can actually use its reaction with iodine to test it. Ethene reacts with iodine, forming diiodoethane, but ethane does not react with iodine. So to test the gas that we produced, I add a few drops of dilute iodine water to the test tube. You can see that it starts out as a pale yellow-orange color. However, after shaking the test tube, the solution becomes colorless. What has happened is that the yellow-orange iodine is reacting with the ethene to produce diiodoethane, which is completely colorless. Let's compare that to a test tube full of just normal air. You can see that nothing happens and the yellow color just stays the same. However, we can also prove that this reaction doesn't happen with alkanes. Here I have 2 test tubes full of propane and butane, and you can see that when iodine water is added, the color does not change. Well, now you know how to make ethene gas and how to test for it. Well, that's it for this video.